So in this part of Lecture 11, what we want to develop is additional graphs, pressure composition graphs, in which we plot not only the total pressure as a function of mole fraction in the liquid, but also total pressure as a function of mole fraction in the vapor. These are examples of pressure composition phase diagrams, and what we want is or what we're going to get is a bubble point line and a dew point line and a tie line. Those are the three things that we want to develop in this part of the lecture. So again, let's see what we're up to here. We had in the previous part of the lecture, we had a graph like this. We had the total pressure as a function of mole fraction. We'll use that symbol X as the mole fraction of a component 1 in the liquid phase. And just to refresh our memory, what the system is here is like this. Here you have a liquid here you have a vapor up here, you have two components here, you have two components there. There's a dynamic equilibrium between the two. So if you change the mole fraction of component 1 here, you change the amount of 1 up here, and that will change the total pressure. And Root's law says that for an ideal solution, the total pressure is a linear function of the mole fraction in the liquid phase. So this would be total pressure for Root's law. Now what we want to do is to have the same kind of pressure composition phase diagram where you have total pressure, but now instead of a plot of total pressure versus mole fraction in the liquid phase, what we want is a plot of total pressure versus mole fraction in the vapor phase. And we'll use the symbol Y to denote vapor phase. That's what we want to develop. And just to remember, it's a two-component system, two components, 1 and 2. So that means that we can easily translate this from a mole fraction of 1 to a mole fraction of 2 by saying 1 minus, because 1 minus mole fraction of 1 is a mole fraction of 2. Okay. Well, so how do we want to get there? How can we express mole fraction, total pressure as mole fraction in the vapor phase? Well, let's start it this way. We know that the pressure of component 1 above the solution is the mole fraction in the solution times the vapor pressure of pure 1. This was Raoult's law. We also know that the vapor pressure of 1 above the solution is the mole fraction times the total vapor pressure. This is Dalton's law. So both of these quantities equal the partial pressure of component 1, so we can say x1 p1 star is y1 p total, or in other words, the total pressure is equal to the mole fraction in the liquid phase divided by the mole fraction in the vapor phase times the vapor pressure of pure 1. So if we could just figure out to express x as a function of y, then we can replace that, and then the total pressure will be a complete pressure of y. Okay, so we're looking for an expression x equals some function of y, and plug that in here. Okay, well, let's go ahead and do that. We know that the mole fraction in the vapor phase, we just said, was the partial pressure in the vapor phase divided by the total pressure above the solution, and that's equal to that over the total pressure. And we have two components. It's just the sum of the partial pressures. Again, that's the total pressure being the sum of the partial pressures. That's Dalton's law. And that, of course, assumes that we have an ideal solution, and the gases behave like ideal gases and so on. And we know that from Raoult's law that the partial pressure above the solution is just the mole fraction in the solution times the pressure of pure 1 divided by P1, the mole fraction in 1, times the pressure of pure 1, plus P2 is the mole fraction component 2 times the pressure of pure 2. Raoult's law. And that's what Y1 is equal to. Well, there we go. If we rearrange this, we have an expression of x1, the mole fraction of 1, as a function of Y1, which we can then put into this expression and get total pressure as a function of just the mole fraction in the vapor phase. We can get rid of the mole fraction in that phase. Well, let's go ahead and do that. Actually, we know we can replace this. We can get rid of the x2 by having x1 p1 star over x1 p1 star plus 1 minus x1 p2 star, because we have a two-component system and the sum of mole fractions have to equal 1. Okay, well, let's see. Well, let's just go ahead and multiply this thing out. We go on to the next page. Actually, we can probably make this just clean this up a little bit. So if we multiply P2, we got that, minus P2, and so on. So we can re-express this. So Y1 will be equal to x1 P1 star divided by P1 star minus P2 star x1 plus P2 star. All right, so there we go. So we want to solve this x1 equals some function of y1. All right, well, let's go ahead and do this. You can skip to the end if you're not interested in this derivation. P1 star minus P2 star x1 plus P2 star. Y1 multiplies all of that, and that's equal to x1 P1 star. Let's pull out the x1 and multiply by y1, so we have x1 y1 P1 star minus P2 star plus y1 P2 star is x1 P1 star. Okay, we're getting close, so let's put that x1 over there, and that will be so we got x1 y1 P1 star minus P2 star minus x1 P1 star. Let's put that over there. We're isolating the y1s over here, so we got y1 P2 star with a minus sign. Don't forget the minus sign. And let's see. Let's pull out the x1. So we got x1 times this whole thing. y1 P1 star minus P2 star. We pulled out the x1, so this is just minus P1 star. That's equal to minus y1 P2 star. And we'll put this thing in the denominator here. So we end up with x1, the mole fraction of 1, is, let's see, that doesn't look very clean. There we go. x1 is equal to, let's see, y1 P2 star over, let's see, P2 star minus P1 star y1 plus P1 star. There we go. So we have x, the mole fraction in the liquid phase, as a function of the mole fraction in the vapor phase. All right. So we go back over to our equation that the total pressure was the mole fraction in the liquid divided by the mole fraction in the vapor times the partial pressure pure 1. Okay. We know what that is. We're going to plug that right in there. y1 P2 star divided by P2 star minus P1 star, Y1 plus P1 star. That's X1. We multiply that by P1 star, and then we divide by Y1. Look at the Y1's canceled out. So the total pressure is, that Y1 canceled out, so it's just P1 star, P2 star, divided by, that Y1 went away, so we just have P1 star plus Y1, P2 star minus P1 star. There we go. So the total pressure is a function of the pressure of the mole fraction in the vapor phase. And recall that Raoult's law, the total pressure as a function of the what's going on with my thing here? The total pressure is a linear function of the mole fraction in the liquid phase. This is P1 star minus P2 star X1 plus P2 star. There is a total pressure versus mole fraction liquid phase. That's linear. But what's interesting is that the total pressure is not a linear function of the mole fraction in the vapor phase. All right, so that gives rise to bubble point line, dew point line, and we'll talk about the tie line in just a second. All right, so here's a plot. We change the ink color here to black so I can draw on that. So here's a typical plot. This is benzene toluene, which is almost an ideal mixture. Benzene toluene, two-component system. So what we're plotting here is the total pressure above the solution as a function of the mole fraction of benzene, mole fraction component 1. This here is Raoult's law. So this will be plotted versus the mole fraction of benzene. So this now is a function of the mole fraction in the solution. Now if we take the same data and plot it as a function of mole fraction in water, in the vapor phase, this is mole fraction in the vapor phase, you don't get that straight line, you get this curved line, this red line that goes up like this. All right, so this is called the bubble point curve or bubble point line. That's what that is. And this is called the dew point line. All right, so let's see what happens if we, let's say we're start here, right up here. And remember that we're assuming we have constant temperature. So remember, for a two-component system, we have 3 degrees of freedom. We're reducing that to 2 degrees of freedom by holding temperature constant. So the 2 degrees of freedom are pressure and composition. Okay, so let's start up here at this particular pressure and at this particular composition. All right, so this would be about half and half. So you got half benzene and half toluene. So there's a new, let me change the ink color here, a new symbol here that a lot of textbooks use. So Z will correspond to mole fraction, total mole fraction. So combine both the liquid and the vapor phase and get the total mole fraction. So we have like X is the mole fraction in solution, or the liquid. Y corresponds to vapor, and Z corresponds to the total mole fraction of a particular component. All right, so this is benzene. We're sitting up here. It's all liquid. Now what would happen if we lower the pressure? Let me change the ink color again so we can see that. So what would happen if we now lower the pressure? We're lowering the pressure. We're still up here in the liquid region. So this corresponds to, at a particular composition and high enough pressure, we're in the liquid region. If you now start lowering the pressure above the liquid, what's going to happen is that you're going to enter this region here. This region here is a two-phase region. So here you have liquid plus vapor, when you're in this particular range of composition and pressure. Now as you go further on down in pressure, you have in this region where you're in total vapor. So there's no liquid present. So here you have two phases. Here you have one phase only present. Up here in this region you have one phase only present. And within the bubble point and dew point lines, that area, you have two phases present, liquid plus vapor. Now the reason why this is called a bubble point line and a dew point line, think about this. So here you have all vapor. When you just hit this line, some of the vapor starts to condense. Just like in an early morning, if you have a very humid air, and the night air cools it down, when you wake up in the morning, there's dew on the ground. So this represents that transition from just all vapor to actually some sort of condensation. And then as you go here, you have liquid plus vapor. When you go further up, what's happening is you're starting to, go from all liquid to vapor. You get bubbles. Maybe you think of this like as boiling. Okay, so that's what the bubble point line is, what the dew point line is, and the different phases. You can also say start at this particular point in the phase diagram where you have, say, no benzene, all toluene. It has that vapor pressure. If you go across this way, when you cross the bubble point line, you go from an all liquid to a liquid plus vapor. And now you go from liquid plus vapor to all vapor as you increase the composition, percent of the mole fraction of benzene. Okay, so we know a little bit about bubble point lines, and we know about dew point lines, that and that. What about tie lines? All right, it's a horizontal line giving composition of the vapor and liquid for a given composition, and the lever rule is related to tie lines. So it looks like we're sort of used up here, so let's go here and draw another bubble point and vapor point diagram, bubble point, dew point, and we'll reproduce this. So we go this way, straight line, that's your, for ideal situation, that's your bubble point line, and down here is your dew point line. Something like that. This is total pressure, and this is composition of some particular kind. So suppose you're in here in the two-phase region. We'll put Y1 or Z1. That'd be the composition, total moles. So suppose you're right here at this particular composition. So that corresponds to a particular value of Z, total moles of component 1, both in the liquid and the vapor. Now, what you do, let me change the color here again. Let's go to, say, yellow? Yellow. How's yellow? We go across here. So we're right there at that point, that particular composition and pressure. We go across here. If you take this down and drop it down here, this gives you the composition at this particular liquid vapor, the composition in the liquid phase. And if you take this, extrapolate this down, this gives you the composition in the gas phase or the vapor phase. This is called a tie line. And if, for example, you say this is the length of there, and this is the length here, let's call that L2. So there's a relationship between the length of these lines, and these are called tie lines, and the amount, total amount in the vapor phase and in the liquid phase. Now to derive that a relationship, let's consider the following. The total number of moles in the system times the mole fraction, the total mole fraction of component 1 in the solution. We're using the symbol Z for that. That is equal to the number of moles, the total number of moles. This is both components, both component 1 and 2, that are in liquid phase, times the mole fraction of component 1 in the liquid phase plus the total moles in the gas phase times the mole fraction in the gas phase. That should be a Y. Total moles in the gas phase. We can also say that the total number of moles in the system, component 1 plus 2, times the mole fraction of 1, so this will give you the number of moles of component 1. That's equal to the total number of moles in the liquid phase times the total mole fraction of component 1, and plus the number of moles in the gas phase times the total mole fraction of 1. So let's equate these two. So the total number of moles in the liquid phase times x1 plus the total number of moles of the gas phase times y1. That's equal to the total moles in the liquid phase times z1 plus the total number of moles in the gas phase times z1. We can rearrange this. Let's say the total number of moles in the liquid phase times, say, x1 minus z1. So we took that one and put it over here. We're going to take this one and put it over there. Take out the total number of moles in the gas phase, z1 minus y1. All right, let's look at these two quantities. Well, this we'll call L1, and this we'll call L2. x1 minus z1, that is, x1 minus z1. By the way, this, we said we started out with this as z1, so this is z1. So x1 minus z1, and this would be z1 minus y1. So these are just L1 and L2. Okay, so we have L1 and L2. So what we end up with is the total number of moles in the liquid phase times L1 is equal to the total number of moles in the gas phase times L2. And this is called the lever rule. It has to do with levers or levers, I guess. I'm pronouncing like an English person. So if this amount decreases here, then the number of moles has to increase, just like a lever. Okay, so we know something about, go back here, tie lines and the lever rule. 1 and 2, this is the end here, corresponds to total moles. The moles of component 1 plus the moles of component 2. So I guess there's a little change in notation that's needed. This is N in the liquid times L1 equals N in the gas phase times L2. Okay.